morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to discuss with the FM demodulators. So, there are different types of FM demodulators, practical FM demodulators that can be built into various ways, like first one is FM Slope Detector, FM Balance Discriminator, Quadrature Demodulator, PLL, that is a very famous kind of FM demodulator, that is phase lock loop. The next one is the zero crossing detector. So, first we will see the FM slope detector. It performs the FM to AM conversion. Now, when the signal is converted to AM, so we can use any kind of AM demodulator from where we can reconstruct the input signal. So, the input to this particular block diagram is since it is a FM demodulator, so the input will be an FM signal. Then there is a filter which is been drawn and whose transfer function is given by this equation, that is HF. Then inductance and capacitance are connected in parallel. The output will be a AM signal. So, this will be a AM signal. Then it is passed through an envelope detector, that is a kind of AM demodulator, and here we are having a message signal which is denoted by MT. So, this is one way of reconstructing the input signal, that is message signal from FM. Now, next is Foster-Seeley discriminator, that is also known as a balanced discriminator. Now, the input to this discriminator is again it is an FM signal. Now, here a transformer is connected, so at the input side, and this will be the center tap transformer. The secondary winding is connected in a center tap form. So, what is being how these two center taps, that is the upper side and the lower side, these two are centered at two different frequencies. The upper side is centered at set at frequency greater than FC, that is the carrier frequency, and this is set at frequency lesser than the carrier frequency. So, inductance, capacitance, again the filter is connected over here, then two diodes are there, like this one is D1, this is D2, and then again and low pass filter is connected, which will going to filter out the higher frequency terms, because when we are going to derive the equation for this type of demodulator, we are having higher frequency terms, that is 2 omega CT or 4 omega CT. So, it has to be filtered out because we only want the message signal, the DC term. So, this will be a low pass filter, that is a combination of resistance and capacitance. And then we are having a XT signal, which is nothing but the message signal that we require, and it will be multiplied by a constant, that is again a DC term, that is an integer value. So, the working of this particular type of circuit diagram is demonstrated by this transfer characteristics, that is also known as S curve. So, this work when FC, when F naught is greater than FC, and this is the curve when F naught is less than FC, that is the positive side of the carrier frequency, and this will be the negative side of the carrier frequency. So, that is the case for balance discriminator. Now, next is the quadrature demodulator, the block diagram. So, FM signal is converted into PM also. So, PM signal is used to recover the message signal. So, in the first type, we have converted the FM signal to AM, then we have used an AM kind of demodulator. In second case, we have used the balance slope detector, that is a Foster-Seeley. Third type of demodulator is quadrature demodulator, where we are going to convert the FM signal into PM, and then we are going to recover the message signal from the PM signal. So, this is the input to this is again an FM signal. It is directly applied to a phase comparator circuit, where it is a phase detector. Then it will be applied to a phase shifting circuit. So, this is a signal delay T naught times carrier frequency FC, which will be equals to 90 degrees or pi by 2. So, pi by 2 a phase shift will be applied. So, at the input to this phase comparator circuit, two signals are applied. First one is the FM, another one is the phase shifting circuit, that is pi by 2 phase shifted version of this FM. The phases of these two signals are compared, then it will be PM signal will be generated. Then it is passed through a low pass filter, and then we are having this message signal, that is the output of this PM signal. Now next type is using XOR gate for phase frequency detector. So the purpose of this is to produce a signal, current or voltage proportional to the difference in phase or frequency between two input signals. So this is, you can see that these are the two input signals, that is the working of the previous diagram. This is the empty signal, this is pi by 2 phase shifted version of the empty signal, as you can see over here. So you can see that these are the two phase differences. So this is applied to this phase detector, and we are having this V output. So that can be generated using this XOR gate also. So the input through this XOR gate will be 0 0 0 1 1 0 1 1. So since the operation of the XOR gate is nothing, it is when the two input bits are different, the output will be high. When two input bits are same, then the output will be low. So that is the case of the XOR operation that we can use over here. So this is how we are going to generate the message signal using FM. Now next is Quadrature Demodulator implementation. So to this there will be an FM input which is applied to this phase shifter or the delay time. Then here you can see that three components are connected in parallel, that is RLC, which will make up a tank circuit. This is connected in the feed forward method, and you can see that this is connected to this multiplier. The output will be an FM signal. Then it is passed through a frequency limiter. And then we are having this message signal, that is the output of this particular type of circuit. Now next is very important kind of FM demodulator, that is phase lock loop. Now phase lock loop works on the principle using three very important components, like first one is the phase detector, second one is the loop filter. Now loop filter is also known as low pass filter. Next one is the voltage control oscillator, which is connected in the feedback path. So this is the main diagram of this PLL. Only three components are used. This can be used as a bias generator. So the input frequency is nothing. This is an FM signal. It is applied to a phase detector, where it will going to detect the phase, and then it will be error signal will be generated over here. This will going to make error signal must be, ideally error signal should be 0. So what is the main aim of this phase lock loop is that whatever will be the output of this voltage controlled oscillator, it has to be compared with this input frequency, and we have to make this error signal to be 0. When this is equivalent to 0 or approximately equal to 0, then we can say that the circuit will be phase lock. So that is the main purpose of this phase lock loop. Now at the output, this will be the output signal is phase, since it is a phase discriminator, then the bias generator will be there. So that is the main principle behind PLL. Now next type of demodulator will be a zero crossing detector. Now what is zero crossing detector? Whenever the signal which is to be demodulated is crosses the origin, then it will going to detect that yes, the message signal amplitude will be, it will going to plot proportional to the input signal whenever it crosses the origin. So zero crossing detector are also used because of the advances in the digital integrated circuits. These are the frequency counters designed to measure the instantaneous frequency by the number of zero crossings. The rate of zero crossing is equal to instantaneous frequency of the input signal. So that is known as the zero crossing detector. So this is the block diagram how we are going to perform the zero crossing detector operation. Like this one is the FM signal, it is applied to an limiter, that is amplitude limiter, then there will be a zero crossing detector is there, this will be a multi vibrator, then this is a averaging circuit is been there. So these are the output of these at every step, like this will be the FM input. Amplitude limiter will going to convert the sinusoidal waveform into a square waveform. Then whenever it crosses the origin, a function will be generated. As you can see, this crosses origin, this crosses origin, a function will be generated. Now here a multi-vibrator is there which will going to convert this impulse function into a pulse of width tau, means this will be the starting edge of the pulse. The width of each pulse will be same, as you can see the width will be tau, and this is how we are going to generate an averaging circuit, because since it is been closer to each other, then that will be higher frequency, and here higher amplitude is there, positive amplitude, and here the amplitude will be less, so the amplitude will be less in the averaging circuit. So that is the output of the zero crossing detector. Now we will going to discuss some of the examples that how we are going to solve the numerical. Like first one is a single tone FM signal. Its standard equation is given by 10 cos 2 pi 10 to the power 60 plus 8 sin 2 pi 10 to the power 3t. So we have to determine the carrier frequency, modulation index, frequency deviation, that is delta f, and we have to calculate the bandwidth of the signal, that is of the phi FMT, bandwidth of this particular kind of signal. So first we have to write the basic FM equation, because whatever equation is given in your numerical, you have to write the standard equation from which you have to compare, and some of the parameters you can find out after comparing also. You do not need to solve the equation, you can find out using the standard equation also. So the equation for the FM will be AC cos omega CT plus beta sin omega MT. This will be the standard equation which is given in the numerical, that is 10 cos 2 pi 10 to the power 60 plus 8 sin 2 pi 10 to the power 3t. So by comparing these two equations, we can find out that this will be the carrier frequency, this will be the message signal frequency, that is 1000 Hertz. The modulation index is given as beta, which is 8. The peak deviation delta f is equals to beta into fm, that is 8 into 1000, that is 8000 Hertz. The bandwidth of the signal is given by 2 fm into beta plus 1. So that will be the case for bandwidth. That is being calculated using Carson's rule. So this is a very famous formula how you are going to calculate the bandwidth of the FM signal. Now next important topic that is related to FM is preemphasis and deemphasis. Now since the signal has to travel over a channel, whether it is a guided channel, whether it is an unguided channel, we have to increase the amplitude of the signal prior to the modulation, and then whatever we have increased, we have to compensate it at the receiver side after demodulating the signal. So that is the main idea behind preemphasis and deemphasis. So this is the waveform of interference versus frequency. This is FM signal, this is PM signal, FM with preemphasis and deemphasis. The channel noise acts as interference in FM and is uniform over the entire bandwidth. Voice and music have more energy at lower frequencies, so we need to emphasize their upper frequencies by filtering. So whatever signal which is being required at the low frequency range, it has to be increased, or artificial boosting of the signal is to be done, means we have to increase the amplitude of the signal prior to the modulator. So this is the main idea behind preemphasis and deemphasis. So preemphasis filter, it is a kind of filter only which will going to amplify the signal amplitude. It is a combination of resistance and capacitance, and in series resistance again is connected. Then it is passed through an FM transmitter. Then a channel is there. Now at channel, the noise will going to affect the quality of the signal. This is the AWGN, that is additive wide Gaussian noise. Then it is applied to an FM receiver. The output of the FM receiver will be a deemphasis filter, which is a combination of resistance and capacitance only. So filtering improves signal to noise ratio in the FM transmitter. So this is preemphasis and deemphasis in FM. So the typical filters, this shows the comparison. These are resistance, capacitance. This is resistance which is connected in series. H omega, that is the transfer function of this particular filter, is V output upon V input, that is the output voltage upon input voltage, which is 1 plus j omega R1C divided by 1 plus j omega R1 parallel with R2 into C. So this is the graph of this particular type of filter. Now next one is the deemphasis. This is much more simpler as compared to the preemphasis, where resistance and capacitance are connected over here. So V out upon V in is 1 upon 1 plus j omega R1C. So this is the deemphasis of this filter. Next is comparison between NBFM and WBFM. So modulation index, as I have told you, that it should be less than 1, but it can be less than 0.3 also. This is the standard way. It can be greater than 0.3. Maximum deviation, that is delta F, is 5 kilohertz, and here the maximum deviation is 75 kilohertz. Range of modulating frequency is 20 hertz to 3 kilohertz, and here it will be 20 hertz to 15 kilohertz. Its bandwidth is approximately same as that of AM bandwidth, that is 2 FM, and here the bandwidth will be twice of delta F plus FM. The applications of this NBFM are written over here, that is short range ship to shore communication, etc. And here it will be entertainment broadcasting, can be used for high quality music transmission also. So that is the comparison of NBFM and WBFM. Now next is comparison of AM into AM and FM. So as we know that in this we have to change the amplitude of the carrier signal proportional to the message signal, and here we have to change the frequency of the carrier signal proportional to the amplitude of the message signal. Its modulation index is AM upon AC. Its modulation index is delta F upon FM. Its bandwidth is 2 FM. Its bandwidth is denoted by Carson's rule. Only 2 sidebands are there, and here it will be infinite in case of the WBFM condition. This is some numerical related to FM. Now last numerical is related to the Armstrong method, which I have discussed in the previous lecture also, where 2 frequency multipliers are there like this, n is equals to 4, n is equals to 5, and then we can calculate the various parameters considering the standard equation for the FM. So in today's lecture we have discussed FM demodulator, some numericals related to this particular topic. Thank you.